Hi, welcome to lecture 4 part 2. We'll still be talking about stochastic process, random signals. But in this lecture, we'll be talking about how it will behave when it passes through a linear time invariant system. Okay, so let's look at your stochastic signals. So just a review from the previous lecture, we defined what is a random process. We define the different properties, ergodicity, stationarity, wide-sense stationary signals, the properties of wide-sense stationary signals, and how we characterize the bandwidth and power of your random process. So the random process or the spectral density can be defined from the autocorrelation function of a random process. Okay. So now, just recall the LTI system response. In the time domain, your output is equal to the convolution of the impulse response and the stimulus. And in the frequency domain, the frequency Fourier transform of the input multiplied by the Fourier transform of the impulse response is equal to the output Fourier transform. And that's how a linear time invariant system works. Right. Does this apply though for random signals? Fortunately, we cannot use it for random signals. For one, we cannot define x of t in the first place. If we can define x of t, we don't know what x of f is. So any form of analysis, time domain, frequency domain, Fourier transform, differential equations, we cannot apply it for random signal inputs, okay? So how does a random signal behave? Okay, so we'll only consider wide-sense stationary signals. So in all practical signals in the real world are wide-sense stationary. So for a random signal, recall that its Fourier transform, its autocorrelation rather is only a function of parameter tau, which corresponds to the time delay between the snapshots of your autocorrelation function. Okay. So let that x of t be a wide-sense stationary input to a stable and deterministic LTI system. At the very least, uh, we know the impulse response of this LTI system and it's stable. Okay. Then the cross correlation between the output and the input is just the convolution of your impulse response and some x of tau minus alpha. Okay. So this is the convolution of this x of tau minus alpha here is actually your autocorrelation function of the input. So the cross correlation here at the output here. So uh, that is the output here. So it's just convolve this with this. Okay. And if we put it in an anti-causal system, h of minus tau, or your response just flipped, okay, then we actually get ry of tau. Okay. So that will be equal to h of tau convolved to h of negative tau convolved to the autocorrelation function of rx of tau. And this is how random signals behave in an LTI system. So if we decompose that, if you look at it in the frequency domain, we have a power spectral density or an energy spectral density passed through an LTI system. You'll have the Fourier transform of the cross correlation function. Okay, and then if we since this is h of negative tau, we flip it in time. The Fourier transform of that will be equal to the conjugate. Then basically the output power spectral density, the power spectral density of the output or the energy spectral density of the output is equal to the magnitude square of the frequency response multiplied by the energy spectral density of your input signal. So what does that mean? It just means that, let's say h of t, the system is a filter. If we let a random signal pass through that filter, some of its frequency components will be scaled accordingly based on the response of the filter. Some of it could be increased, some of it could be decreased, some of it could be rejected. Okay? So basically, let's have an example. So we have a Whiteson stationary random signal, an autocorrelation function defined by this. It is processed by a causal filter. So a causal filter, recall that practical systems, it always starts at tau is equal to 0, okay? Or t is equal to 0, rather. And the response of the filter is equal to this. Determine the autocorrelation function at the output. So how do you solve that? So based on the given earlier, on our derivation earlier, the autocorrelation at the output is equal to the magnitude square of h of f multiplied by Rx of tau. Okay, and if we get the uh, if we get the Fourier transform of Rx of tau, which is a cosine function, then that's equal to 1/2 times 1/2, so it's 1/4 times delta of f minus fc is delta of f plus fc. Okay, so if we plug that in, it's basically magnitude square of h of f times 1/4 times this, and by the shifting property of your delta function, it will be equal to 1/4 times h of fc squared, excuse me, plus h of negative fc squared. Okay, and that's it. That's how you solve it. This is the solution. Okay, I just wrote it in the slides, right? So, all right. So this is the Fourier transform, the energy spectral density. To get the autocorrelation of the output, you get the inverse Fourier transform of this, and it looks like a cosine function also. We get this value at the output. Okay? So the random signal is filtered in some way. Okay? So now let's move on to the operations of random signals. Random signals can be superimposed if x of t and y of t are jointly Whiteson stationary. Then if we add them, okay, the autocorrelation function of the resulting signal is just the sum of the autocorrelation function plus minus depending on the sign. They're cross correlation functions. Okay, and if you get the Fourier transform of that, since these are all just linear combination of each other, you just add the corresponding Fourier transforms. Just a special case, if v of t and w of t are uncorrelated or zero covariance, and uh, the expectation of x of t times expectation of y of t is equal to 0, then the cross-spectral or cross-correlation terms vanishes. So basically, just these all just be 0. Okay, and with that, if v of t and w of t are uncorrelated, then basically the power spectral density of the two signals will just add on each other. Okay, so just quoting the words of Professor Escoto, the great Professor Escoto, there is no superposition of power. Okay, you can't have in a circuit perspective, if you have two sources, there's a power contribution from source 1 and there's a power contribution from source 2. So there's a power on source 1 on R, Okay, there's a power due to source to on R also. And if we get the individual powers contributed by V1 and V2 to R, and we add them, you still won't get the total power as if we connected them in series. Okay, there's no superposition power. In reality, the power, if we superimpose signals, the power will depend on the correlation between the two signals also. Okay. And the power will only be superimposed if the signals are uncorrelated to each other and that their means are equal to 0. Okay. So now what if we have the product of random signals? Let's say they're independent and jointly White and stationary. If we have a multiplication of those signals, we have the following property. The the autocorrelation rather of the output will just be a multiple of the two. And because we multiply them in the time domain, in the autocorrelation function, then basically we convolve them in the frequency domain. Okay. Now, we will now talk about the modulation property. Let z of t be equal to some x of t times a cosine function. Right? This is actually an important property for communication systems. So x of t, so let x of t be a White and stationary signal, and phi may be uniformly distributed from 0 to 2 pi and independent of x of t. The autocorrelation of z of t is equal to 1/2 of the autocorrelation function of x of t times cosine 2 pi fct. So this signal right here disappears. The random, it doesn't matter what phase your cosine function starts with, the autocorrelation function will still be the same, with the corresponding spectral density right here. A note, your Sx right here will be shifted upwards and downwards in frequency. Basically, if this is your power spectral density, the resulting modulated version will look like this. Basically, an image of your signal will be split into two right here, as you can see here, right here, and an image will be formed. You can call it an image. So one of them will be at negative FC and the other one will be at positive FC, and both of them are scaled versions, right, based on this 1/4 right here. And this is how modulation affects your wide sense stationary signal. Okay. Now, let's move on to a special type of process, okay, the Gaussian process. And this is an important process that happens in most electronic communication systems. So what is a Gaussian process? It's all marginal, joint, and conditional probability distribution functions for your random signal at the snapshot t sub I are Gaussian functions. Okay. So basically, normal distributed, all random variables, all snapshots are normally distributed. So the process is completely described by the mean and the autocorrelation. If the autocorrelation is can be expressed this way, then V of t1 and V of t2 are uncorrelated and independent. If V of t is White and stationary, then it's also strictly stationary and ergodic. So it's only uh, one of the few cases where when if your signal is White and stationary, then it is also ergodic. Okay. And finally, any linear operation on the Gaussian process produces a Gaussian process. So if you pass it through a filter, then it will still be a Gaussian random process. Okay? So now let's look at noise. The noise, as you recall, refers to the unwanted random signals that tend to disturb the quality of the received signal in a communication system. Since it is a random signal, it can be analyzed through its statistical properties. So since it's a random signal, well, we'll talk about statistical properties. The common probabilistic models are used here, uniform and a Gaussian probability distribution function. Okay. So a type of noise that is modeled in communication systems is the white noise. What is it? The white noise is a signal that changes very fast. So that means it becomes uncorrelated after an infinitesimally small time delay. So that means its autocorrelation function is a delta function. If you have a slight time delay, your white noise, your random signal, will now become uncorrelated with itself. And this produces, since this is a delta function, it produces a constant magnitude, sorry, it produces a constant Fourier transform. There you go. That means the energy spectral density of white noise is consistent and constant over all frequencies. Right? We call this a flat spectral density over a wide frequency range. Basically, all frequency components are of equal proportion. Right? Hence the name white. So it's white as in white light, because it's white light. You have it contains all color of wavelengths, all frequencies of light, right? And it appears white, right? So the value of this N naught right here depends on the temperature of your system. So N naught is equal to KT normally, where K is the Boltzmann's constant and T is your absolute temperature. And it's actually dependent on how an electron behaves in a wire or in a conductor. The electron randomly moves depending on the temperature because of temperature. Okay, so it randomly moves if there's no electric field inside it. It randomly moves, it creates noise. Okay, so for example, I'll show this to you during the lecture, so don't worry about that. Okay, so now what happens if we filter the white noise? So if we filter the white noise, recall that if we have an input signal here, the output signal will be equal to your magnitude squared multiplied to your input signal. Since noise is constant over all frequencies, then the output signal after filtering will become some form of colored noise, since some parts of the frequency will be scaled depending on h of f. Okay? Since the spectral density will not be flat for the output. So if you filter a white noise, so you introduce correlation in time, since autocorrelation is also modified. Okay? So because of that, we can model all if we have a white noise and we have an LTI that has some form of frequency response, we can solve for the equivalent bandwidth of noise. Okay? We can compute the average power of the filtered white noise. That's the first. You just get the area under the curve of the output here. So that is the noise power. Okay? So this is the noise power. Sorry. Oops. Due to the even symmetric nature of your filter, you can simplify this expression into this. So you start the integral from 0 to infinity instead of negative infinity to positive infinity. And we can now define the equivalent noise bandwidth as B sub n equal to this, where we assume a response that is ideally low pass. Okay? And this low pass here with bandwidth Bn, ideal low pass filter with bandwidth Bn, has the same area as your integral of h of f squared. Okay? So these two have equivalent areas. The height of these two are equal to h max. Okay? And now we can get the equivalent noise bandwidth based on that. So we can now model the behavior of the system as an ideal low-pass filter with bandwidth B sub n, based on the noise equivalent bandwidth. Okay? Finally, additive noise is noise that adds to the information. This is common in all communication systems. You have a signal because of the noise of the random movements of electrons. The output is just a corrupted version of the input because of the added noise. And the total power can be found by averaging y squared of t. Okay? So some assumptions here: n of t is ergodic with zero mean, and these two signals here are uncorrelated. Then that means this term will disappear. And basically, the output power is equal to the signal power plus the noise power. And noise is usually modeled as an additive white Gaussian noise. Okay? So that's the end of this lecture. If you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.